So hello everyone. So today we have the pleasure to sustain Manuel Diaz, the Master Thesis Defense. So hi everyone in the internet. So I have to read something in Spanish just for protocol and later we can just start, okay? Entonces, en este solemne acto académico que preside el decano, el decreto universitario 001827 del 7 de enero de 2019, el señor Manuel Benjamín Díaz Zúñiga rinde su examen de grado ante la comunidad académica como último requisito para optar al grado de Magíster de nuestra casa de estudio. El examen consistirá en la defensa pública de su tesis de grado titulada Light Structures and Topological Defects Self-Induced by Light in Liquid Crystal Optical Systems. La comisión del examen es presidida por quien les habla, la doctora Carla Germán, e integrada por los siguientes académicos: Jaime Anguita, Michelle Kowalski, Ki Hyun Wee, y su director de tesis, el doctor Max Clerc, académico del Departamento de Física de la Facultad de Ciencias Físicas y Matemáticas de la Universidad de Chile. El señor Díaz tendrá un máximo de 45 minutos para exponer un resumen de su tesis. El examen continuará luego con las preguntas formuladas por los miembros de la comisión. En general se estila de más lejos a más cerca. Y luego con todos los presentes, y solo los que tienen grado de magíster o más. No pueden preguntar las personas que no tienen grado de magíster, como mínimo. ¿Ya? Así que, Manuel, tienes la palabra, tienes 45 minutos.
Well, thank you.
Yeah.
Well, thank you everyone for being here. My name is Manuel Diaz Zúñiga, and today I'm going to present my thesis dissertation titled Light Structures and Topological Defects Self-Induced by Light in Liquid Crystal Optical Systems. First, I will give some brief introduction, and then I will present my main results and the conclusion for this work. Okay, well, light is a well-known natural phenomenon that can be described by Maxwell's equations. A light beam is an electromagnetic wave that can be written in terms as a planar wave solution expressed by the electric component, and it's composed by different K aspects. The first one, the envelope, is a complex field that accounts for the transversal electromagnetic spatial mode that is divided in an amplitude related to the light intensity profile that we observe with our measures, and associated phase field that can create some different structures, as I show here. The other term is the polarization. Describe how these fields oscillate in the transversal field. Depending on this component, we can find different state of polarization. For example, linear state polarization, circular state with this spin on light, among others. And the propagation mode that indicates the evolution in space and time of this solution. Well, light structuring is the manipulation and modification of its properties, such as amplitude, phase, polarization, combination of both, among others. And one of the classical experiments that show this effect is Young experiments, where two coherent sources of light interfere in the free space, generating this structured one-dimensional pattern in the light intensity that reveals the wave nature of the light. In the last decade, scientific advance enabled richer light structures with different fundamental implications and, of course, technological applications. To generate these structures, we use, well, there are various methods to generate it. I focus on Bird-Engine material. These alter the light propagation depending on the wavelength and polarization, are characterized by, we can observe usually this material as these multicolored samples or these samples with superposition of image. And they have different refraction indices depending along different directions. For example, X, Y, Z. And for this work, I focus on uniaxial Bird-Engine materials. These materials present just two different refraction indices, the ordinary and the extraordinary, and their respective refraction index and isotropy. How we can describe the light-matter interaction? Well, to modulate it, we consider a planar wave solution, and after interact with our material, we represent the output light beam via this Young matrix operator. It is composed by a different element that depends on the alignment of the elements in the Bird-Engine material respect to the optical axis. We have this rotation matrix that project the components in the principal axis depending on the angle phi. And this matrix that generate a fair retardance between the components of the electric field depending on this angle capital theta. And also carrying a dynamical phase used for interact with the material. Okay, this operator I called the W during this presentation. And to characterize the state of polarization, we define what we call the exposed parameter. Each parameter accounts for different properties of the light. E0 accounts for the light intensity. E1 accounts for the horizontal and diagonal components. E2 accounts for the, E1 accounts for the horizontal and vertical component. E2 the diagonal component, and E3 the helicity of the beam. And for a fully polarized beam, when we normalize by the light intensity, we obtain this relation. This describes an sphere in the parameter space that is called the Poincare sphere. Here we can find, for a full polarized beam, the state of polarization well defined as a point on its surface. Finding different regions, for example, the equator is related with a linear state of polarization, poles relate to the circular state of polarizations, and the rest find a different elliptical state of polarization. Okay, other important topic for this work is the topological defects in continuous media. These are localized regions where the topology presents a non-trivial configuration, and in 2 dimensions described by vectors or complex field, it may appear different topological defects, in this case phase singularities, where is, or also called vortex defects, where the phase in this position is undefined and around the phase appears in a spiral structure. And for the continuous, to keep the continuous of the field, the amplitude decays to 0. It's characterized by this number, the topological number that accounts is the number of that counts the number of winds the phase around the phase singularity. Here I present different non-trivial state of polarization for these vortex defects, and this number have important properties. It's also called the topological invariant because this remain constant under smooth perturbation. As I showed here, when we calculate this number, the state equal to 1. We can find this state in optics, called optical vortices. This appears in the envelope of our light beam, and the topological charge adhere a physical meaning. Is related to the orbital angular momentum of the light, and its states have different technological application. For example, in optical trapping and displaced microparticles. In quantum computing, generating qubits of entangled states described by this orbital angular momentum. In free space communication, encoding information in these singularities and using this topological protection to transfer this information through the free space under perturbations, turbulence, etc. And in astronomical measurements, where the coronagraphy methods use this vortex to surprise high signals, for example, from a star, to observe lower signals, for example, for a planet. Okay, to generate this state, we rely to another important concept for this work, the geometric phase. We can understand this easily with an example. I can define a vectorial field in a non-Euclidean space, for example, a sphere, and I can translate this vectorial field in this trajectory, this closed path. Then when the system complete the loop, occur a phase delay. This is related to the geometry of the system. That's why the name geometric phase. And it's very popular in quantum mechanics, where Michael Berry showed that this is a gauge invariant solution, a physical solution that appears in quantum states, also called Berry phase, but was firstly discovered in the fields of optics by Shiva Ramakrishnan and Pancharatman, who showed that it states when we have 2 light beams that undergoing different polarization transformation described by these trajectories, this adheres a relative phase that is proportional to the area enclosed by this path, okay, as I showed here. This is used to generate optical vortex by these elements, the Q plates. Q plates are Birnbaum material that present a chiral structure. This chiral structure transfer a geometric phase for circularly polarized beams that is proportional to the transversal angle phi. impressed in the sample. That means this chiral structure is transferred to the face, creating an optical vortex with a well-defined topological charge. Okay, well, I use liquid crystals. Liquid crystals is an aggregation state of a matter that exhibits properties, both solids and liquids. That means flows like a fluid, but have elastic properties and other optical properties like a solid. Is present in different mesophases, depending on the symmetry and the order in the system. I focus on the nematic phase. The nematic phase don't present a spatial order. That means don't create lattices on the space, but a group of molecules can be aligned in a common aberrant direction, described by this mesoscopic element. And we describe it by this anisotropic element, like a grain of rice. And for the nematic phase in a constant temperature, we describe this state by what we call the director vector field. I use, in this case, liquid crystal cells. This is a thin nematic liquid crystal layer, sandwiches between these two glass substrates coated by this transparent conductive layer. When we apply voltage, this voltage generates an electric field inside of the cell, and depending on the dielectric properties, the molecules alter its charge distribution and be in alignment depending on its distribution. For example, for positive dielectric anisotropy, we observe the molecules aligned parallel to the electric fields, and for negative, we observe these molecules are aligned perpendicular. We use this property for negative dielectric constant in these cells with anometropic anchoring. That means the molecules are fixed by chemical treatment perpendicular to the walls of the cell. And when we apply voltage, the electric torsion tries to reorient the molecules, but the elastic force tries to maintain the alignment imposed by the bonders. This balance generates a transition in some threshold that is called a Frederick transition, where the molecules are reoriented. This reorientation uses perpendicular to the electric field, but have freedom in the transversal plane. Across this plane, for a continuous media by fluctuation, we can find different domain of orientation, do some regions oriented in that direction, other in that direction, etc. And when these domains collide, we observe the different defects on the system, and the stable defects are these, the umbilical line defects that for a quasi-dimensional analysis can be interpreted as a liquid crystal vortex or matter vortex in the system. We experimentally observe this transition using the polarization optical microscopy method that, or also called a cross-polarized method. That is, we put the sample between two linear polarizators, and if the sample presents some Birmingham, we observe something in our camera. For the case of a vortex effect, we observe this swastika texture. Okay, and this is an experimental observation of this transition. This is also a topological transition. That means the topology in the system is altered, generating these effects. And we can observe these effects start to interact. This interaction decreases the number of vortices, this chiral structure in our Birmingham materials, and is well characterized by this interaction, the distance between the opposite vortices decrease following this power law. This is due to the nonlinearity of the system and the topological charge associated. This is a problem because if we want to use this chiral structure to generate optical vortices, we must sustain and control this vortex liquid crystal. And for that, I use a liquid crystal light bulb. This is a liquid crystal cell that includes a photosensitive layer. This photosensitive layer convert light intensity profiles into a photoinduced voltage proportional to the light intensity. In this case, with that, we can generate a localized reorientational transition in this region, for example, but also the electric field inside of the cell is altered by this inhomogeneous voltage in the system, generating a transversal shape of the electric field with this vertical structure. The interplay between both effects of the light generate a localized vortex solution in the center of the light beam. Okay, this was previously reported in this reference and show that this chiral structure generates also an optical vortex in the light beam that induces it. That means the light induces a vortex defect in liquid crystal, and then the same defect generate an optical vortex in the light, being a self-induced vortex generation via this self-organized type couplet. Okay, under this context, we define this general objective that can be expressed in terms of key research questions. The first is which self-organized phenomena emerge under external topological forcing in liquid crystal systems. The second, what are the physical mechanisms responsible for the transition between different states in optical bulbs? And the fifth is what are the different optical response of light-induced states in optical bulbs? To respond to that, I divide this work in two parts. The first part is called light structure self-induced liquid crystal light bulb. It's structured in 7 chapters. The 5th chapter is related with this solution that's called Rayleigh vortex that appears by this topological forcing in a system, and it differs with the standard vortex liquid crystal. And here we characterize the transition that was completed in these 2 publications, one in a scientific journal and another one in a conference proceeding. The second chapter is related to other previous reported solutions, shadow vortices. This appears outside of the illuminated region. It's stabilized in the shadow region. That's why it's named. And in this part, we try to characterize the mechanism behind its stabilization and its experimental facility to observe it. Concluded in a conference proceeding. In the 3rd chapter, we explore the question what happened about the Fourier transition. We observe when we have a reoriented state with a defined trivial topological solution. We observe the localization or other type of solution without presence of phase singularity. And we wanted to understand why and what are the optical effects. In the 4th chapter, we explore what happened when about this Fourier transition, the light is enough to break the symmetry in the system and generate a localized topological transition. When experimentally we observe the appearance of a vortex dipole, a bare vortex anti-vortex effect that stabilizes a bounded state in the system, and we try to understand the mechanism behind this interaction and how the light alters the vortex interaction. In the 5th chapter, I explore the question what happened when an optical vortex interacts with a liquid crystal light bulb. Q-plates usually alter the topological charge in optical vortex, but in this case, by this self-organized Q-plate, appear other more complex states in the system that coexist. And we try to understand the origin behind it and the optical response in the system. In the 6th chapter, we explore a more fundamental question: what is the real nature of vortex interaction? Usually, the previous report showed that this interaction generates a radial force proportional to the distance of the vortex, but experimentally, we observed the interaction describe non-central trajectories on this system, that we describe by an interaction with the global reorientation in the media that accounts for a particle field coupling in the system, and we characterize its mechanism experimentally and theoretically, completed in this submitted work for peer review. And the last chapter focusing how is the light structured by our our light-induced vortex liquid crystal light bulbs. We usually focus on the topological charge, but the complete structuring is until under study. For this, we observe the generation that is known as vectorial beams, and we find mechanism to transit between different polarization states that was concluded in this manuscript under preparation. This is the first part. The second part is divided in 2 chapters and related with other type of phenomena that we observe in liquid crystal light bulbs. The fronts. Fronts are nonlinear waves that connect different states of equilibrium. And when we add a non-reciprocal interaction in a discrete stable system, we observe the propagation of unidirectional fronts that are controlled by this non-reciprocal interaction. And we modulate its system and characterize its behavior theoretically and experimentally. That was concluded in these 2 publications, one in a scientific journal and other in a conference proceeding. And the last chapter is focusing how do discretization and non-reciprocity affect the propagation of fronts. In discrete system appears some phenomena that the propagation fails. It's known as pin-in-the-pin transition, and we characterize the mechanism behind it concluded in this scientific publication in a scientific journal. This is the complete outline. This due the quite long work in this thesis. I focused for this presentation in 2 chapters. Okay, for this development, I employ and mount this experimental setup. This includes a diode pulse solid-state laser. This laser allows us to control the light intensity with a linearly polarized Gaussian profile that we pass through this microscope objective that expands the beam, making its light intensity nearly to an homogeneous profile. And then we alter its light intensity profile by this element. It's a spatial light modulator that can structure the light, in our case, modulating the amplitude. That means we send some mass in this with a software in this device, and it's projected into the amplitude. And then we project this image in our device, in the liquid crystal light bulb, and we observe its light matter interaction with this CMOS camera, usually under a cross polarization. This is the real experimental setup. Okay, this one is the liquid crystal light bulb. This is a small device. And this is an experimental observation of this light-induced vortex by a Gaussian beam under cross polarization. Okay, to describe its system theoretically, we usually describe the dynamics of the vector by the Frank-Gaussian equation coupled with an electric field, but this is a highly nonlinear system. For that, we reduce our model close to the Fourier transition by an amplitude minimal equation with an universal properties. In this case, is the Girdler-Landau type equation, where this is a complex field. This field A is a complex field that accounts for the projection of the reorientation amplitude in the transversal plane. The first term is the bifurcation parameter that indicates the transition, where this parameter is below to 0, we are below the transition, and when it's positive, we are above the transition. It's divided in 2 terms. The homogeneous term that make a reference with the Fourier threshold, and the other term that accounts for the photo-induced voltage produced by the light intensity profile. This term accounts for the elastic anisotropy on the system that is due to the anisotropic structures of the liquid crystal molecules. Different deformation is related to different energies. And the last term accounts for the second effect of the light intensity, this structuring in the transversal plane of the electric field inside of our sample that acts in this dynamical system as an external topological force. For this reason, we call this equation a topologically forced Girdler-Landau type equation. When we perform numerical simulation, we observe good agreements with the experimental results for this model. This is a good model for us, and usually, for simplicity, we define what we call the polarization field phi, the C, that is an approximation of the polarization optical microscopy analysis. Okay, I will start with the first chapter for this presentation. Sorry, the geometric phase localization induced by light in liquid crystal bulbs. Here, I focus on the question, what is happening about the Fourier transition? Because usually we set the system below the Fourier transition and we cross its threshold locally by the light effects generating this non-trivial topological state. But what happens when we are above this threshold? The system adheres an orientation state that is defined in the stationary solution as a homogeneous state without phase singularities. And when we apply the light intensity, it breaks the translational and the phase symmetry on the system. It generates a localized solution in the center of the light beam, and we try to understand why does this occur and what are the optical effects of this solution. To respond to this question, I perform numerical simulations of our dynamical model, considering the bifurcation parameter positive in the whole space. And starting for a trivial initial condition, we observe the generation of an inhomogeneous region in the phase field that accounts for this solution that we observe experimentally. To understand its solution analytically, I perform a perturbative analysis, considering, of course, this parameter positive, and considering the topological forcing small. This is the term that that breaks the symmetry on the system. Okay, for that, using the perturbative method, I find the zero order solution and the first correction. The zero order solution is this. We can find this solution that its amplitude is proportional to the bifurcation parameter. That is something that we know. And the phase accounts for a global phase orientation, phi0. It is related to the global initial state. Okay. And when we perturbate our system with our first correction, considering this complex field written as in the real and the imaginary parts, we obtain this complex system of equations. But considering the isotropic limit and a global phase orientation in the phi0 angle, we can reduce this equation to this one, and we can solve it, obtaining these solutions. This solution is written in terms of the modified Bessel functions and also the light intensity profile. But the important thing is the solution have information about the global orientation. Okay. When we perform numerical simulations and plot this analytical result, we observe a good agreement between these solutions. Okay, showing that this is a solution of the system. It's not a numerical tool. And this global phase allows us to obtain information about the global system. Okay, if the system presents, for example, a global angle 0 degrees or minus 45 degrees diagonal orientation, the localized solution adheres these structures, these different structures. This anisotropic structure is rotated with this, depending on this global angle. And for the experimental results, we perform this gradient of density that fixes the global orientation and then apply a Gaussian beam. We observe the inhomogeneous localized structure in the phase rotate respect with the angle that we fix with our gradients, showing that its relation exists in the system. For the optical aspect, I modified the experiment, implemented this interferometer system. This is a Mach-Zehnder interferometer with a small tilt angle beta. Okay, this system works like this. We generate a circular polarization beam to adhere this geometric phase on the light and divide these beams in two arms by this beam splitter. One arm interacts with the liquid crystal light bulb, adhering the geometric phase, and the other one is tilted by this small angle. And when these two beams interact, generate a interference pattern, finger pattern, that have information about the geometric phase. For this analysis, I neglect the dynamical phase because it's small in compared to the effects of the dynamical phase. Okay. And well, this light intensity profile, this finger pattern profile, can be modified by animated processing, making it more simple, and we can express the sinusoidal function in terms of our measurements. Okay, in terms of the light intensity that we measure. And to extract the phase information, I employed the Hilbert transform that when we obtain the complement sinusoidal function, and with that, I can reconstruct the geometric phase in the system. The problem here is, well, this is the pattern that is generated by the geometric phase, this distortion pattern. But the problem is this expression carries this spatial mode of the finger pattern. And to eliminate it, we take another measure that is a reference without this phase distortion. Okay, and using the same protocol, we obtain finally our expression for the geometric phase estimation. And to check this protocol, I consider an input geometric phase like is produced by our system. And after the protocol, the phase estimated is this. We observe a little difference that could be related with this dynamical phase that I neglect. For the experimental observation, here is the solution under cross-equalization system, and this is the finger pattern solution that we observe the distortion of the pattern induced by the geometric phase. after this image processing, we can, using the Hilbert transform, we can obtain the geometric phase that we estimate with this protocol, showing that effectively we generate an inhomogeneous geometric phase in the light beam. In summary, about the Fourier transition, we observed that the system, this this extended nonlinear system, when it's forced with a topological forcing, could not respond with a topological solution as this inhomogeneous phase. Our mathematical model allows us to predict this solution, relating this with the global orientation that is present in the liquid crystal system. And the localized phase solution generate geometric phase in the system. And it could be used for different applications. For example, for inhomogeneous birefringent material can be used for generate waveguides induced by geometric phase that was previously reported in this reference. Okay, the last part of this thesis is related with the light-induced polarization transition from scalar to full Poincare beams in optical bulbs. Okay. For that, first I will introduce what is a vector beam. Usually I previously described what is called a scalar beam. A scalar beam present an homogeneous transversal polarization distribution that allows us to separate the envelope from the polarization. But in general, for a more complex structure, it cannot be separated. Okay, the envelope is related with the polarization, generating these complex structures. These present an infinity of possibilities. Okay, and we can characterize it by the symmetries present in the system. For example, for azimuthal symmetries, we characterize what we call cylindrical vector beams. And other possibility is for the interest of this work is the appearance of different states of polarization, linear, circular, elliptical, present and distributed in the transversal plane that we call a Poincare beam. How we can generate it? Okay, well, what happens when we alter the polarization? This is the operation that applied the birefringent material and describing in terms of the Stokes parameter follow this relation in terms of the initial state of polarization and the final state of polarization. This relation generates a geometric space is a beacon where the center is placed in the initial state of polarization with the inverse helicity. That means if I start with a left circular polarization, the center is placed in the right circular polarization. And the intersection expresses the region where the final state of polarization could be found. Okay? Well, couplets alter the polarization structure. If I consider a linear input and interact with a couplet, we observe this vectorial beam. This, in the Poincare sphere, describe this curve. This is a Viviani type curve, okay? But the chiral structure impressed by the Q-plate generate a field of the birefringent curve previously generated by the birefringent material. That means this point is related with this state of polarization, this other point with this one, the other point with this one, filling the curve in the Poincare sphere. We want to measure that in our experiment. For that, I employed this method to measure the polarization state. This for measure using a linear polarizer, putting horizontal, vertical, diagonal, and other measure, including a quarter wave plate. With this, I can reconstruct the Stokes parameter and plot this state in the Poincare sphere. To the structuring in transversal plane, I define windows of pixels that I calculate the Stokes parameter and plot the states in the Poincare sphere, observing these results for experimental measure, considering initial state polarization linear, circular, and elliptical, observing that our system is different. Don't create a curve, a birefringent curve, create a surface induced by the birefringents in the Poincare sphere, and we want to understand why it happened. Observing different patterns in the transversal polarization. Okay, to understand it by the light matter interaction on the system, I consider the phase retardation is expressed in terms of the orientation of our liquid crystal molecules. And for a small refractive index anisotropy, we can reduce this integral for this expression that still depends on the axial angle in the C direction. But our dynamical minimum model relate the director vector with the complex fields, finding this relation with the angles. The transversal angles is directly the phase of the complex field, and the axial angle is expressed by this complex expression. But when we replace this in the integral, we can solve and obtain an analytical solution that relates the phase retardation with the amplitude of our complex field. Now, finding this direct link between the light matter interaction and our model, we can study what happened in our system with localized vortex solution. Okay, and we observe the generation of this surface in the Poincare sphere that is in good agreement with our experimental results. The important thing is it is due because the phase retardance depends on the amplitude of orientation. And for this forces system, the amplitude is proportional to the bifurcation parameter that have the light intensity profile. That means for more light intensity are more reorientation on the system and describe a more bigger curve in the Poincare sphere. And when we are far from the center of the light beam, we find a small curve in the Poincare sphere. This is not a behavior present in Q plates and wave plates where the phase retardance is constant in the space. Is what we call a D plate, a doubly inhomogeneous wave plate that depending on the phase retardance displaced in the traversal plane, we observe different curves in the Poincare sphere, generating the image that I previously showed in our system. Checking that in the dynamical system. This is the numerical result. I plot the state of polarization close to the light intensity and far from light intensity, observing that I previously mentioned. This continuous deformation of the Beer-Vinger curve generated this surface that we observed previously. And this means the light intensity can alter the polarization structure in the system. According when we increase the light intensity, in this case related with the parameter mu1, we observe an increase of the amplitude of orientation on the system. That means we can translate from a scalar beam to a fully polarized beam. That means adheres all the possible state of polarization distributed in the transversal plane for linear, circular, and elliptical states. These are numerical results, and these are the experimental results that shows the same behavior. We can control the transition for the scalar to full Poincare beam states by changing the light intensity. To quantify and characterize this transition, I calculate the area enclosed by the polarization distribution state in the Poincare sphere. For that, I consider the initial state and define every point by spherical angles. And with that, I can calculate the area that enclosed this distribution. And after some discrete analysis, I could plot the effective area that uncovered the Poincare sphere, observing when we increase the light intensity, the mu1 parameter, we start from a 0 area enclosed, effective area enclosed. That means a scalar solution. And when we increase the light intensity, we observe the transition to a full Poincare beam. Okay. This is a comparison between the numerical and experimental results by this analysis with different initial state polarization, observing the same transition. Okay. But also the versatility of our model that is not depending on the alignment on the system can create lattices of vector beams. For example, with two light beams, not collinearly alignment, for different light intensity, we observe different structure around the light beam, structures in the polarization. So that means we can create lattices of Poincare beams distributed in the transversal space for more complex vectorial beam solutions with, well, different possible implications. In summary, this inhomogeneous reorientation of the light-induced vortex generates a point carabines in our system, we find a direct relationship between the amplitude model to the light matter interaction. We explore different mechanisms to this control in the polarization structure in the system, and show the versatility of the liquid crystal light bulb to generate different and complex vector structures. Okay, and in conclusion for this work, responding in the previous questions, research question, which self-organized phenomena emerge under external topological forcing in liquid crystal system? Yes, during this work, I find different states that emerge by this external forcing, Rayleigh vortex, shallow vortex, theoretical, and other more complex structure like these Rosetta vortices induced by this OIM type profile. What are the physical mechanisms responsible for this transition between different states in optical system? We find and use different tools of nonlinear physics to explain the mechanism of stabilization, emerge, and control of different states in the system, like vortex dipole, like this front non-reciprocal propagation, among others. And what are the different optical response in the light-induced states? Well, that was I present in this presentation, observing the generation of inhomogeneous geometric phases and also light structuring in polarization that we can control by different control parameters in our experiment. Well, that was my presentation. Thank you for your attention, and I'm ready for any question.
Okay, thank you so much, Manuel. So we should start with the questions from the commission. So in order to, well,
We usually
make this like by the furthest away.
she starts the question. So in this case is Professor Kihu. Okay, so Professor Kihu, this is your time for make questions.
Okay, thank you. Thank you, Manuel. It's very good series of work. Can you hear me?
Yeah.
Hear me well?
Yeah. Sorry.
Okay. So one question I think that I want to ask you is, now you did a lot of work, so mostly curiosity driven. So what is a major goal you want to achieve? So through your dissertation, is that towards a particular application or towards a particular thing that you want to understand, right? So what is a major objective of your dissertation? And then second question is, given that your very interesting result, what is the major impact that you can expect? For example, if that's some fundamental understanding, fundamental discovery, and what are the fundamental discovery? What is the impact to the field?
Well,
two questions first.
Yeah, sorry. Well, thank you for your questions.
Yeah.
First, I consider the main goal of my work during my master thesis is related to the optical response in this liquid crystal system. Usually, previous my work, we focus just in the liquid crystal interaction, how to describe this nonlinear system, etc. But with this, we explore more the optical implications, finding this field in GROW, that is the study of structural light in different aspects, polarization, amplitude, generating more complex structure. And I think this is one of for me, the most important aspect in this work. For the same reason, I present different works here related to optics, and the impacts that I consider for this is the versatility that present in the device. Usually, for generate this structural light, we impress some samples fixed in the system, for example, couplets, other dielectric surface that can generate this structure. But by self-organization, understanding it and controlling it by this external function, we can explore a world of different possibilities: geometric phase, inhomogeneous phase, this structurally light, other more complex bonded state of vortex in the system, etc. I think that could be the most relevant impact. And also the theoretical implication in this work, I don't talk about it related with the vortex interaction and the front non-reciprocal propagation, but also during this work, I working theoretically, numerically, and experimentally, trying to explain the mechanism behind its behavior, finding, in my opinion, important contributions in the understanding of non-reciprocal discrete system and vortex interaction.
Okay, good. So I think that in your interferometry measurement, you measure the geometric phase, try to separate from dynamic phase. Which part I'm not fully catch how you did that? How did you separate it and determine that's a geometrical phase and not the dynamic phase when you measure the
I could
using interferometry?
let me
Could
move
you-
to the presentation. Sorry.
Yes.
Yeah, I could share. Sorry. Well, I could share this. Can you see the? Sorry.
Yeah, I can see that.
Give me a second. Sorry.
Yeah.
Now, yeah, perfect. Well, first, the first try to estimate its geometric phase was just comparing the numerical simulations. I don't plot it here, but when numerically we can control what phase are impressed in the pattern. Okay, and when I printed the dynamical phase, I didn't observe more relevant deformations in the phase that I estimate, and also the phase that is adhered. And when I plot just the geometrical phase, I observe the structures, and that's what the first argument to neglect this interaction. But the second one was when we find a relation between our dynamical system and the light matter interaction, I can find that also we can relate the dynamical phase with our dynamical model. Okay, showing using the same, following the same derivation, I obtain that the dynamical phase is proportional to the reoriented amplitude in the liquid crystal system. Okay, that means we usually consider that the amplitude of reorientation is small. That means this phase is small respect to the other type of phase that cover the whole domain for minus p to p. And that's why the arguments to neglect it, but also generate deformations. As I show in this numerical simulation, we observe difference between the input and the output geometric phase estimation. But that's why I neglect it.
Okay. So in optical vortexes, for the Q plate, the Q plate is already something like they sell as a product. So what is new for the Q plate part? You compare with the Q plate.
Well, compared with a Q plate, also compared to a spatial light modulator that can generate optical vortices also, I consider that the most significant advantage of our system is the alignment, okay, and the self-organization. Because usually when we want to generate an optical vortex, we need to align the chiral structure with the optical axis. And this is a problem for more complex experimental setups. For that, the liquid crystal light bulb just acts as a self-organized interaction that every time appear the optical vortex in the center of a light beam. It depends of the alignment. And it also allows us to generate more complex system. As I showed, we can send lattices of beams generating a lattice of vortices, and we can change for different subject of study, depending of what we want, just changing the input intensity.
Okay. One basic question. For optical vortexes, right? So you use a Q plate, you can generate optical vortexes. What is the topological charge in the optical field and a topological charge in the liquid crystal field? How are they related? These two charges.
Yeah, they are related by this expression. Okay, this is that I call the sun-orange transformation. Generate this geometric space that is proportional to the helicity of our circularly polarized beam, the charge implicit in the Birevingen material, okay, and it's multiplied by 2. That means if I have a topological charge a 1 in the Birevingen material, I obtain a topological charge equals 2 in the light. Okay, and in the matte liquid crystal system, the stable charge are positive 1 and negative 1. With this method, we could just create charge in the optical field with +2 and -2. But for liquid crystal light bulbs, the charge induced is always positive. That means for the liquid crystal light bulb system, we just create optical vortex with a charge +2.
Okay. Okay, so these are factor 2. Where this factor 2 come from?
Yeah. Here.
So the optical charge, the optical vortex, the charge of optical vortex is twice of the
twice of the charge impressed in the Birevingen. Yes.
Charge.
Twice, yes.
Where this 2 comes from? Why is a factor 2?
Why 2? Well, this is
why there's a factor 2.
Why is the number 2? Sorry, that's the question. What is the factor?
Yeah. Why is the number?
Why is the origin? Okay.
Yeah.
The origin is due also the Birevingen material, the elements that compose it, and the liquid crystal don't present a direction. That means we usually describe it as a vectorial field, but it don't present a sense in the direction. That's why if we rotate our system in 140 degrees, we obtain the same behavior, and this is transferred in the information to the light. Okay, when we when we generate its geometrical phase, depending on the chiral structure, do the molecules generate this? Well, the elements in the Birevingen material generate its rotation. Do the symmetry is multiplied by this factor 2.
Okay. So I think I'm done with my question. Thank you.
Thank you, Professor. And now it's the turn of Jaime, ¿verdad? Turn of Jaime Anguita.
There. Thank you very much. I really enjoy your presentation, Manuel. So I have a few questions, some that are sort of basic and others that are more advanced. not many. And maybe I will, touch a few of the ideas that Professor Kiho just mentioned. Let me start with the first idea about the vortices. When the optical bulb imparts a phase dislocation, right, onto the beam, what happens to the transfer intensity profile, the intensity profile of the beams at the beam's axis? And what is the physical principle requiring this?
Well, the physical principle is related with the light-matter interaction. Oh, sorry, first, thank you for your question. And it's related with the light-matter interaction. I have a slide with this. When we perform circularly polarized input, we transform it following this expression. Sorry, I will find the important one, this one. Okay, the result output fields after this light matter interaction have this expression. Okay, this is used for interact with our system expressed in terms of the Jones matrix operator. And here appears different aspects that not only alter the polarization and the phase, also alter the light intensity. We observe the envelope appears this term, this sinusoidal terms that depends on the phase retardance. And as I show, this phase retardance depends also in the molecular orientation. For that reason, we usually observe different inhomogeneous pattern in the light intensity, also impressed in the fringe pattern in the interference method.
Good. So at the end, what do you see in the intensity profile?
Well,
what
we
do you
see
capture with the camera?
We capture
At the axis.
Yes. Sorry, what?
What do you see at the axis of the intensity profile when you take a photo of that?
We observe just this intensity profile impressed in the envelope. That's why to extract and apply this process to extract the phase, including the finger pattern, I need to make an image analysis because this is the image that I observe. For example, close to the light intensity, I observe more intensity impressed in the pattern, but outside I cannot observe much of this. For that, I subtract the background in this processing and extract the binarized pattern to reconstruct this sinusoidal function. But I observe every change.
Yeah, and when you make that observation, right, with your camera, what has happened to the phase? Is there an evolution that happens? At what point in space you have to apply your measurement so that you can see that? Can you do it right away after the evolve, for example?
That is an interesting question. We, in principle, we have to observe immediately after the liquid crystal light bulb. The problem is by the structure of the device, we cannot observe it and observe some evolution in the propagation of this solution. For that, in the experimental system, I employ different different optical elements to project its image in the camera for more longest distance. I use this 4F relay optical system to project it, but of course, it's evolved in the propagation, and we neglect its effects when we measure it on the camera. But optical vortices have this topological protection, and that's why we also measure it in our experimental system. But it's an interesting question. Explore what happens when it's propagated and its structure interacts with other structures that we impress in the system, etc.
Yeah, but you would expect that even there is interaction, the axis should remain as a topological discontinuity, right? So it should remain as that.
Yeah.
Okay. So my second question, if you go back to page 17, I think it's almost the same as that I think it's the same experimental setup.
Yeah. This is
Okay.
the 17.
Okay. So how do you use the SLM? At the beginning, you were saying that I don't know if you use it all the time, and if you do, what is the
Yeah.
purpose of that?
The purpose of the SLM is modulate the amplitude that we project in the light intensity on the system. It acts as a versatile device for us. That means I can send a Gaussian beam, a flat beam, a lattice of beam. That's is the purpose for its use. But we could, for example, use other modulations that present the SLM, for example, in phase to generate optical vortex and observe what could happen if it effectively interact with our liquid crystals.
Yeah. So let me stop you
But
there. Let me stop you there.
yeah,
So
sorry.
when you say you apply for example, a vortex, so what do you actually do with the SLM? You change the intensity, you change the phase. What does
Yeah,
it
I
do?
changed the intensity profile.
So this SLM in particular has is an intensity modification or is a phase change SLM? Is it?
It both alter the phase and the amplitude of the envelope, but we employ other optical elements to modulate, as the fabricant indicates, to modulate, to use this device to modulate just the amplitude. In this case, we surprise other spatial mode with this 4F system, and we use this linear polarizer to surprise the other structuring polarization that in the configuration that indicate the fabricant. That means the light intensity input must be vertical and the output linear polarizer have to be horizontal. We observe that effectively the image that we send in the software of the spatial light modulator is impressed on the light,
Okay.
but needs
So
more optical elements.
Okay. Where does those changes you apply to the SLM are actually observed in the propagation of the beam? Because if you apply, for example, a spatially phase change across the spatial distribution of phase, right? It is going to be observed as a change of intensity after some propagation distance, right? So
Yeah.
where would you see that is fully developed in your setup there? So after a lens, where?
Well, we consider a length that is displayed by this 4F system, okay,
Uh-huh.
to surprise this interaction. But when we test our experimental device, we don't find other phase structure impressed on the light using these methods. Okay, this is because also in the focus of this 4F system, I surprise other spatial mode that carrying phase information. I
Okay.
use the neutral mode.
Okay. So it is well defined at the focal point
Yeah.
where you
Yeah.
apply that filter. Okay. Good. I have another question. You highlighted very recently that the difference between a standard Q plate and the D plate, the D plate is generated by the light bulb, right? So you highlighted they were different. But since both can support optical vortices, right? How do they compare regarding the degrees of freedom they can offer for example, synthesizing spatially variant polarization states?
How you can compare? Because, well, Q plates also present a spatial variation in the transversal angle, but not in the phase retardance. This alteration also can modify and enrich the optical structure that we observe, but in principle, the transversal structure, the chiral structure, is the same for a Q plate. Okay, but enriched in other terms using the phase retardation.
Okay, so could you say that you can, so which one encompasses the other one. So one of them produces more possibilities than the previous one, right? So is
Yeah.
does D comprise the capabilities of Q-plate?
No, in terms of the polarization structuring, just in that aspect, we can find different. In this case,
No.
generating more complex.
Yes, I know that it's more complex, but for example, can you resemble with a D plate the operation of a Q plate?
Yes, completely. Just considering an homogeneous semi-variable.
So that was my point.
Generalization, yes.
Okay. So what would you do in an
Understand.
experiment if you want to use the D plate exactly as a Q plate?
Well, the D plates are used to fabricates essentially with fixed patterns. Okay, for our case, that liquid crystal light bulb acts as a self-organized D plate. We must to fix the light structure to generate an homogeneous reorientation on the system. For example, sending a flat beam to act as an effective Q plate.
Good, excellent. Okay, yeah, I'm happy with your answers.
Sorry, I can't understand first.
Thank you, Jaime. Now it's the time of Michelle or Mike.
Okay, so this was a very nice talk, and I could understand some of it. But first, I have a comment, and the comment has to do with what you call berry face or berry something berry face, I think.
Yeah.
Could you go back to the slide where you present the Poincare sphere, what you call Poincare sphere?
Yeah, of course. Let me a moment.
So my comment is the following. Okay, there is you make a very nice picture of a sphere on which you move along a triangle. There is a triangle on this sphere, and you move parallel. You make a parallel transform of transport of a vector field. Okay, it comes back with a different phase, and this is related to what is called Gauss-Bonnet formula. So Gauss knew about this. Gauss knew that on the sphere, the sum of the angles of a triangle must be bigger than pi, and this has to do with the positive Gaussian curvature of the sphere, and this excess of the angle, the difference between the angle of a triangle and pi is precisely the area of the triangle on the sphere. And again, it has to do with the fact that there is the very deep geometrical result Gauss-Bonnet, which is called Gauss-Bonnet formula. And I think what you say is correct in the field of optics, but in the field of what is the human knowledge, is not completely correct. This fact was known in the 19th century, the first half of the 19th century, by Gauss. So this is my...
Yes, I present it as from the physical point of view, but of course it was previously mathematically explored and discovered, and it's related with in the optical case, and also in the quantum mechanics is the very phase have more complex explanation. It's not related with an area of the parameter, it's related with this expression. That's why, depending on the system, of course, it's a more general concept, but I just present it as a simplified description for my purpose, but it's correct.
Okay, so you use a theoretical model as the base of your numerical simulations. You call it topologically forced Ginzburg-Landau equation. So I have a couple of questions about this. So first of all, could you explain where it comes from?
The derivation of the model?
Yes.
refer,
Where
yeah.
it comes from? What is because it looks like an ad hoc model, but it has a source, I suspect.
Yeah, of course. I have a detailed slide of this, how we obtain its model. I could explain quickly, of course. We start from the elastic theory related to liquid crystals, describing this free energy related with different deformation on the liquid crystal, splay, twist, and bend, and also adding the electric interaction that I mentioned that alter the charge distribution in the molecule, etc. And then we consider a dynamical relaxation for the vector field. Then imposing this constriction, the vector field don't increase in the model, just is reoriented. We obtain this dynamical equation that describe the evolution of the director vector with respect to when it tried to minimize its free energy with this complex solution. And to obtain my minimal model, I start from the homotropic state imposed by this anchoring, this one, and I perturb it. Applying the nonlinear physics analysis, I consider a small perturbation, and I try to understand the linear instabilization in the system, obtaining that it's occur when the electric field that we apply on the system have this form. This is the threshold, the Frey threshold. Okay. And after that, well, I calculate the effective electric field imposed by the light intensity proportional to this. And after that, I applied a weak nonlinear analysis close to this instability close to this point on the electric field, obtaining this complex equation, but that can be expressed as this. I consider an ansatz for the director vector, which implicates this amplitude of reorientation and a correction, a nonlinear correction, because this is not the solution of the model of the system. And these equations can be written by this expression, this linear equation with the linear operator and the nonlinear correction and the rest of terms. And well, defining another product, we can apply the threshold alternative that imposes a solvability condition for find a solution on this system. And under this solvability condition, finding the elements of the kernel of the adjunct operator, I can calculate defining the complex field A, as I mentioned. I can obtain the reduced dynamical model. Okay, this model is more complex than the model I presented, because I still did some approximations. In this case, I rescale the amplitude, the space, and the time to simplify, to find the minimal expression. And I consider the light intensity is small, approximating the bifurcation parameter to the homogeneous and the inhomogeneous term, and the forcing as this topological forcing. And in that way, I obtain the equation that I showed.
Okay, so this equation is has a variable function that is unknown. You call it A. Why do you call it A?
A? Do you refer why I use this notation, or
Yes.
what?
Yes. Where the A comes from?
A comes from for the amplitude, the transversal amplitude of the director vector. Okay, we consider this ansatz where these fields account for the projecting amplitude in the transversal plane, and I define the complex field by this.
So this is the amplitude equation. It's also called the amplitude equation, and it has certain general character, and you use this in a specific, or you derive it in a specific case.
Yeah.
But basically, this is it's an equation that describes the amplitude of perturbations from some state, in your case, the constant state, near the bifurcation point. Okay?
Yeah, near the bifurcation point, yes.
Okay.
Just near
So
and
in your
outside.
case, this bifurcation point is the point of Friedrich's transition.
Yeah, the point where the electric field occurred the previous expression that I showed, that I call the Friedrich transition. The free
But you
expression.
seem to use this equation kind of liberally far from the Friedrich's transition.
Yeah.
Am I correct?
Yeah. I usually explore experimentally regions far from the Friedrich transition, and its model by the Gisborne-Landau theory remain valid as in a qualitative expression. Even I don't find another instability in the system.
Okay. So what would be the correct
Why it could be correct?
No, what would be correct model to capture
the more complex
quantitatively your phenomena? Because your model and your numerical simulations are only qualitative. They are not quantitative. So what would be the model to
quantitative model.
use? A quantitative model.
Okay, well, the quantitative model in this case is the previous Frank-Osing equation. This is the correct description for the nematic states. Well, considering that the nematics don't flow and don't present, it's under constant temperature. Of course, always we consider some assumptions to describe it, but this is the correct expression, but it just presents an instability for the homotropic state close to this point. Of course, are more instabilities, but usually in the experiments, we vary the solution in a small way. Okay, try to just focusing in the first Friedrich transition. But yeah, this is the complete.
So why you don't use the right model? Let's say the model that is correct.
This one.
What is the difficulty?
The difficulty is that it's a more complex model. It's a highly nonlinear equation that also describes a three-dimensional system. And what we observe usually is the interact with the transversal envelope in the light on the light beams, and for that we reduce it to our quasi two-dimensional system to adhere just the domain information. But also other groups in the world work with this Frank-Osing equation. We find this. We use this point of view to find a universal description close to this transition.
Okay. Okay. Yeah, I'm happy with your answers, and so thank you again for your talk, and I leave space for other questions now.
Thank you.
So thank you, Mike. So now it's my turn. I will try to
quickly because we have a lot of questions. So I was, if can you come back to the slide 13?
Yes. This one.
It's about these jumps when you see like the number of vortices and then like a function of time.
Okay.
So there is like a kind of decision of your vortices in that graphic, like you have 10 and then it jumps to 9 or something.
This is by the discretization in my measures in time.
Okay.
This is not a continuous solution. This is an experimental measurement.
Yes. So in
yeah.
real time, so you are
In real time, I see how this disappear, and some vortex could disappear at the same time. And I cannot control it.
Yes. And I had another question regarding the more closely to the experimental setup. I understand that you are using green light, so the
Yeah.
532.
532. Yeah.
I was wondering, why is that? Why you are using 532, and also whether it would be convenient or not to like imprint some signal with green line, but then with another wavelength.
Yeah, well, that's a good question. I use green line because the photoconductive layer for our device is optimized for this wavelength. Okay, that's why the response of the photo-induced voltage is optimized by this wavelength. But of course, as you mentioned, I could send other light beam with other wavelength that could interact. For example, this photosensitive layer don't respond for red lights in 633 nanometers, and with that it's an idea that we want to implement in the experimental setup, because we use the same light source to pump and observe.
Yes.
That could be a problem, and for that I want to include another laser, aluminum laser, to observe and don't interact with the media. But for that, we are waiting for more optical elements.
Yes, I was thinking exactly that, like
Yeah.
to use one beam, one red light in
Yeah.
order to imprint whatever you want to imprint, and then the observation of the without, you do it with the red, and then you can decouple some problems, observation and observation. Okay, when you say that the system is optimized for green line, can it be optimized for other wavelengths, or is very specifically this
Well,
crystal for
the fabricant send us data sheet that present the optimized wavelength is just 532 nanometers, but we could use other light with different wavelength that where the photoconductor could react, and we could observe the same phenomena.
But it's more about the liquid crystal characteristic inside the bulb.
It's more related with the properties of the photoconductive layer, not with the liquid crystal. Yeah, the photoconductive layer, is restricted.
And I had another question. I think it's related to the question of Jaime, but I wasn't sure if I was following what Jaime was asking. But like, what is the honest comparison between this kind of vortex, the one that you can create by the SLM in your system, and the last vortex that you create with the deep lake and all of that? Like, what is the gain with the vortex that we create, this dynamical vortex, so to say, in comparison to this kind of vortex? What do you gain?
Well, it's the same light structure. The thing is, depending of what we want to study, I change the operation after the light matter interaction. That means, for example, when we generate optical vortices, is, as I show, maybe, let me a second. When we generate optical vortices using these couplet type elements, we alter the helicity of the system, but this not generate a complete translation from for example, left helicity to right helicity. Present different components, one with the initial helicity and other one with the opposite. But we eliminated the initial helicity using, for example, linear or circular polarizers to observe, if we want to observe the optical vortex generated in the sample. But the complete light structuration is more related with the amplitude and in the deep lake case.
It's like another question for me, but do you know if people have tried to create like twin photons, or not twin photons, no, I'm sorry, like entangled photons or entangled paths, not really entangled photons, entangled paths, are using this deep lake? Because this is in my mind, like when you go to the quantum optics regime, you have, for instance, a beam splitter, and this just a split polarization or whatever in two paths. And then you know that when you send like a single photon, you will get entanglement between these two paths. I was thinking if someone has done the same thing, but with this deep plate that you created, so it has to be very small. But this is it's like a young experiment, it's like a double big experiment at the end. But then you will have this entanglement in the photons, but with these different structured areas. So I was just wondering if someone has done this or if you know anything.
Yeah, thank you for the question, but if I'm honest, I'm not completely familiarized with the whole state of art in the structuring light. As I know, people send light, a quantum state of light, and interact with this complex field, maybe with entanglements, but I don't have the reference. But an interesting thing that I find exploring this field in optics is that present interesting properties similar equals to this entanglement in the classical field that some reference called as a classical entanglement, because the non-separability present in the polarization distribution generate that if we alter some polarization, the whole system present a modification, and it's used to improve, for example, optical trapping or more robust free space communication. But it's specifically with the field of quantum optics, I don't find more reference.
Fair enough.
Yeah.
It's not a thing. If I was just asking whether you mean or not, but I can.
But this is a yeah, but it's a more complex field.
I don't have twin photons or single photons, but I do have a squeezing. So I was wondering, for instance, if the problem mixing. Yeah. We also send a structure light, but it's in this spatial, just multimode lane. But this is different. So I know that people has done some vortices with problem mixing, but I was wondering what else. Okay, thank you very much.
Thank you.
Congratulations for your work. In other countries, you will have received a PhD today, and that's the master. So congratulations.
Thank you.
See, this is supervisor.
Okay, so first, I want to send and congratulate to Manuel again for this nice work. If we see the document that Manuel wrote, is impressive in my opinion. I mean, you please have right to write a short thesis, and he wrote a strong thesis in my opinion. So congratulations for that. Also, the private and public defense was excellent in my opinion. So I have to congratulate. And I want to emphasize that Manuel is an excellent and brilliant scientist, in the sense that he will experiment very well. I mean, the experiment that Manuel has studied is noted by Manuel the students. So for us, it's a very new experiment. So this is not trivial for a master thesis. Also, we do a lot of theory, and make a simulation about that. So really, Manuel is a hard worker and scientist. So really, I'm very happy and very proud for him. Thank you. And with respect to the question already have one, so don't speak too much about the non-central force of dynamic of vortices. Could you comment about that?
Yeah, of course. Well, this is related with other part of this thesis dissertation. Is when we explore, well, with other researcher from Spain, when we explore vortex interaction, we find that experimentally, we usually don't observe that a vortex can follow a well-defined central interaction. Let me see if I had this expression. Okay, usually exploring first, it was exploring the theory. The theory say that using the same methods that I explained with our complete model, I could find using the defining a linear product, weak nonlinear analysis, and applying the solvability condition, we can find the dynamical equation for the position of the vortex defects. And it's always carrying this term. This term is related with this phi. This C phase is not the same phi phase that I present as a polarization field. Is related to the global polarization, global orientation distribution that we call a phase excess in the system. This may appear because the phase singularities is not necessarily exactly an alignment between the vortices when it broke the translational and the phase symmetry could be displaced. For example, as this, if we have this phase singularity with this phase jump and other one with the opposite charge with this phase jump, to connect is continuously, the phase must adhere a deformation, and if this deformation is related with this phase that we call the phase excess. Sorry. And usually previous work neglect this interaction, just considering that the relevant part is the radial interaction, presenting a lot of previous work showing that the interaction between vortices is radial. Is showing this power law that following this behavior, experimental result that also show this interaction is well described by this expression, but essentially the arguments to neglect is phase excess, this global phase that interact with the vortices. Is it more faster that have a more fast evolution time than the vortex dynamics? But it is failed. It really is lower, and it lower decay of the global phase remains interaction, particle field interaction in the system that could generate and alter the vortex dynamics, showing in the experimental result that the trajectories that vortex follows are not central, present this deformation. Every experimental observation of this vortex interaction show these non-central trajectories. Okay, and this is due in general is impossible to fix exactly the phase singularities equal to neglect the phase excess, and when its phase excess exists, alter the vortex interaction by this particle vortex effects. And when we measure it, observe that essentially the power law is changed a little. We could modify it in obtaining a more obtaining improved law for the distance between the vortex in time, considering, for example, this phase excess is constant, modifying the power law, and its effect can also be this particle field interaction can be also observed for a single vortex dynamics. Usually, if we consider a single vortex solution, it not break the translational symmetry. That means don't present evolution in time of its position, but experimentally we observe it. It is due the global phase excess that accounts for the global inhomogeneous deformation in the liquid crystal act as a potential that move the particle. Also, it's are alone in the system, just present a single vortex effect. Is the real nature of the vortex dynamics and vortex interaction.
Okay, so with this, we invite all the audience and also Manuel to go outside of the room as a commission. We will make a decision.